Hello everyone, today in this video we'll be discussing the module 3 of Analysis and Design of Algorithms ADA BCS401, and in this video we have the following topics taken from the syllabus, and I will be telling you which are the most important ones. Make sure you watch the video till the end, because if you watch the video till the end you can easily score more than 80% marks in the exam. And if you have any doubt, you can DM me on Instagram. And before starting, please do like and subscribe, it helps me make more videos like this. So without wasting more time, let's get started. The first question, the first topic is the balanced search trees. Okay, we have two things in the transform and conquer. In that, we'll first see about the balanced search trees, which will be having AVL trees. Okay, we'll be seeing what is AVL trees and what are the operations on it. And next we have the heap and the heap sort as well. Okay, so let's have a look. What is a balanced search tree? But before that, what is transform and conquer? Transform and conquer means what? We will transform the tree and then apply the algorithms. Whatever is the thing, we'll be transforming it first, then we'll be applying the algorithm. That is called as transform and conquer. There are two methods for achieving the same. Okay, first one is AVL tree, second is the 2 to 3 tree. Okay, that is comes under the balanced search trees. Okay, so first is AVL tree. Okay, in AVL tree it requires the height between left and right subtree never increase one. Okay, so the theory part you can go through it. I'll just directly come to the main part here with the example. Okay, see here, this is a tree. Okay, suppose that this is a tree, not suppose, this is a tree only. Okay, so in this tree I have to calculate the height at each point. What does height mean? Height means, suppose that I want to calculate the height of this node. Height of this node means, suppose that I'll take this tree. Okay, this is a left subtree and this is a right subtree. If I ask you what is the height of the left subtree height means that where it is starting from, where it is ending to. Take those two nodes, and in between how many edges are there? One edge, two edge. So this subtree's height is 2. Okay, like that here also this subtree's height will also be 2. Okay, and to calculate the height of the tree we have to calculate the difference between these two. Okay, the difference between this and this. Okay, what is the difference between this and this? It is 2 here and it is 2 here, so 2 minus 2 is 0. Okay, now if you consider just this subtree. Okay, so what is its height? This subtree's height is, this one will be having one edge here, so it will be 1 minus, there is no edge here, so 0. 1 minus 0 is 1. This one's height factor is 1. Okay, we'll be taking the height factor. Okay, balance factor or the height factor. That is nothing but the difference between left and right subtrees. The difference between right and left both are 0, so it is 0 here. Here it will be 0 minus 0. Again, here it will be 0 minus 1, which is minus 1. Here it will be 0. See, here it will not be 0, here it will be 2 minus 2. Okay, because 2 is the height from here, 2 is the height from here, it will be 0. Now unless and until the values of the factors are between minus 1, 0 and plus 1, it is fine. Okay, if it becomes like minus 2 and plus 2, we have to do some operations. Okay, this kind of tree is called as AVL tree. Okay, now in case it exceeds, means it becomes minus 2 plus 2, like that things happen. When those things happen, for example, suppose this is the tree. Okay, I have 8, 9 and 10. Okay, I have to insert the values 8, 9 and 10. Now 8 will be inserted here. This works on the principle of binary search tree. You know binary search tree, right? An element is present here and we get another element. We'll check if the another element is lesser than this, we'll put in the left. If it is greater than this, we'll put in the right. That is called as the binary search tree. Here also we'll do the same thing. First is 8, we'll write 8 here. Next is 9, I'll write 9 here in the right side. 10, I'll write 10 here, 10 will come here, right? It will be compared with 8, it's greater than 8, it's greater than 9, so it will come here. Now as you can see, if we calculate the balance factor, okay, balance factor of this is 0 minus 0, so it will be 0. Balance factor of this, it is 0 minus 1, which is minus 1. 0 and minus 1, it's fine, but when we come to 8, it will be 0 minus 2, because this height is 2. Two edges are there between the root node and the leaf node, so this is 2. 0 minus 2 is minus 2. Minus 2 is not a valid one, so we'll have to perform the operation. Now see, this is what? This is the right edge and this is the right edge, so it will be RR. Okay, so there are 4 kind of rotations: LL, RR, RL and LR. Okay, so this is the RR operation. What you have to do in RR? In RR, basically you take the middle element and then turn this in the anti-clockwise direction. That means this thing is there, right? You just push it and make it like this. Okay, here. So what will happen when I push the 8 from here to here? It will come like this, right? Now if we calculate the height, it will be 1 minus 1, which will be 0. sorry, this is 1 minus 1, okay, not 0 minus 0. So it will be 1 minus 1, that will be 0. So the answer here which we are getting, that is fine. It is not minus 2, okay, and this one height is 0 and this one also height is 0, right? Balance factor, it will be 0. So all are 0, so it is a fine tree. Now see what happened, what we did. There was a misbalance. We checked if it is RR. If it is RR means we have to rotate it like this, okay, the anti-clockwise from the top. This is the first case RR. Second case can be LL. Okay, let's take an example. 10, 9, 8, the order of the element. So 10 came here, lesser than 10 is 9, lesser than 9 is 8. So it is an LL. When LL happens, it will be imbalanced because see here, there is nothing here, but here the height is 2. So 2 minus nothing is equal to 2 only. So 2 is not allowed. Okay, the balance factor 2 is not allowed. So what we have to do, take the middle element and push 10 like this down. Push 10 downwards. So what will happen? 9 will be in the middle element and 10 will be pushed downwards. So again it is 1 minus 1, not 0 minus 0. It will be 1 minus 1. It will be 0. So here also 0, here also 0. Now this is a balanced tree. This operation is called as LL operation. Now next is an RL operation. Two rotations are required here. Why two rotations are required? Let's take an example. 10, 12 and 11 is given. I inserted 10, I inserted 12, I inserted 11. 11 will come here because 11 is greater than 10 but less than 12. So it came here. Now I have to do two operations. RL is starting from R, right? So first thing I have to do is convert this tree into RR tree. How will I convert this into RR tree? Now to convert this into RR tree, take the bottommost element. Okay, take the bottommost element and then put it here. Okay, if you put it here, like we'll push it here, what will happen? 11 will come in between 10 and 12. Okay, 11 will come in between 10 and 12. Now this is the first thing you need to do. Now it is in RR position. Okay, always remember last element we will take and push it between these two elements. Okay, so it will become RR. Now again it is imbalanced because it is 0 minus 2. Here it is height is 2, so it will be 0 minus 2. Minus 2 is not allowed. So we already know how to fix RR. RR, what we'll do, we'll take the middle element and we'll push the top element like this. So what will happen? It will become like this. Again 1 minus 1, it will be 0. So this one is balanced. Okay, so this is an RL case. RL case, since first R is there, we have to convert the tree into RR and then we will be converting to normal operation, like how we convert RR to normal tree. Okay, next is LR. In LR, 10, 8, 9, suppose 10, then 8 came and then 9. Okay, so what happened? It was L and R, and the imbalance is also there. Why? Because left height is, what is the left height? To reach the end node between this one and this one, how many edges are there? 1 and 2. So the 2 is here, minus how many are in the right? 0. So it will be 2 only, right? So now it is L and R. Okay, now what we'll be doing, in this case, if it is LR, what you have to do, you have to push 9 in between these two. Okay, the reverse thing. If you push 9 in between these two, it will become LL tree. Okay, because it is LR, right? So first we have to take into consideration L. So LR will become LL tree. Now from here it is very simple. Take the middle element and push this one downwards, like how we did previously, LL conversion to the balanced tree. So it will become again balanced here. Okay, so this is an example of the four operations. These four operations are the most important one, and these are the most widely used in the AVL trees. Okay, so you need to know what are the different operations and what is an AVL tree and how do we convert. Now let's take a normal example. Okay, like the numbers are given here: 5, 6, 8, 3, 2, 4, 7. Now if you want to convert this into an AVL tree, okay, so what we'll do, 5 we have taken, 5 is here, fine, no problem, height is 0, balance factor is 0. 5, then 6 came, so 6 will be here, balance factor is 0 and minus 1, very good. Then 8 came. When 8 came, 5, 6 and 6 greater than, means 6 is lesser than 8, so 8 will be coming here. Okay, because 8 is greater than 6. Now if we calculate the balance factor, here it will be 0, here it will be minus 1 because 0 minus 1, and here it will be minus 2 because 0 minus 2. So it will be minus 2. We have to fix this one. Now if you want to fix this one, first find out what is the operation required. It is RR operation, right? RR, what is the thing I told you? In RR you have to convert, push it like this, right? This 5 will be pushed downwards. So in 5 will be pushed downwards, what will happen? This will happen. Okay, so this is what you have to do from here. Okay, this is the operation, RR operation you will be doing. Okay, ignore this thing L5, R5, this is confusing. Okay, I'll tell you what you need to remember. RR you have to do here and it will become like this. Now next number is 3. When 3 came here, it was attached here and all the height is still balanced. Next, what is the thing? 2 is there. So when 2 came, we attached 2 here. When we attach 2 here, this 2 has become imbalanced. When two things become imbalanced, then the place where imbalance is the closest to the root cause, that will be taken into consideration. So in this case, instead of fixing this one, we'll be fixing this one because it is more nearer to the insertion of that element, due to which the imbalance happened. Now This is which operation? This is LL operation. When LL is there, what I told you, when LL is there, you have to push it like this, right? 5 will be coming downwards of 3. Okay, when 5 will come downwards of 3, 3 will directly be attached to 6. Okay, so what will happen? The 5 came here and 3 directly became attached to the 6. Now all is balanced here, 0 0 0 and 1 0. Now what next? What is the number? 4 is the number. When we see 4, where it has to be? 4, it is lesser than 6 but greater than 3 and lesser than 5. So 4 will be attached here, right? So when 4 is attached here, we'll calculate again. The height here, it is coming as 2. Why? Because the height here will be till the end of the node. Okay, till the end, how many it is taken? Okay, till the end, if we take here, how many will be? It will be 1 2 3. Okay, so 3 is the height in here, and here the height is 1, so 3 minus 1 is 2. 2 is not allowed here. When it is not allowed, we have to do the operation, which is we have to check which operation we have to do. Okay, so in this case, the operation which will be required is, first it is L and then it is R, right? LR operation we have to apply. Applying LR operation on this, I told you LR we have to do two things. First convert into LL and then we have to convert into means normal we have to convert. Okay, so when we apply LL operation on this, okay, first this is L, this is R. Okay, if you want to apply LL operation, what we do, we had previously done 5 like this, right? If you remember the LR operation, what we used to do, the last element which is there, that we has to be inserted between the 6 and 3. So when we insert 5 between 6 and 3, what will happen? It will become 6 5 3. But one issue will be there. 6 5 3 will be there, and 5's left child will be 3, and 5's left child already 4 is there. So 3 and 4 will become merged, but we cannot merge here. So basically what we do here, 5 will be inserting here and 3 is here. Greater than 3 is 4, so 4 will be coming here, just exactly how it can see here. Okay, so this is the thing which will happen. That is the first step. Okay, beside 3 4 will come here, and 5 is still in between these two. Now still in between these two means LL operation is there, right? When LL is there, what you have to do, you have to convert it like this, right? 5 is here, you have to push it like this. So when you push it like this, at the right side of the 5, 6 will be there and 8 is always there, so it will be like this. So now 5 6 and 8 will be here, and the previous one which we had done, which is 3 will be here, and the right child of the 3 will be assigned as 4. This is the LR operation. Now RL operation, what is the element after the 8? 7 is there here. Last element we are getting 7 is here. So 7 will be inserted here. Now the imbalances happened here. When imbalances happen here, check which imbalances happened. RL imbalances happened. When RL is there, you have to put this here, right, in between 6 and 8. So when you put in between 6 and 8, we'll be getting 6 7 8, and this is RR operation. When RR operation is there, this has to be pulled downwards, right? So 7 will be in the middle, 6 will be pulled downwards, and 8 will be here as usual, right? So this is the thing here, 7 and 6 will be pulled here, and the 8 will be as usual, and the remaining thing whichever is there, that is exactly as it is. Okay, so this is the AVL operations. 4 operations are there: RR, LL, and LR, and RL. Okay, you need to know very well, and they can ask you in the exam about like this, their element they can give you and try and tell you to calculate with how many rotations you can convert into an AVL tree. Okay, next is 2 to 3 trees. So 2 trees means having 2 nodes, binary tree. Okay, like normal, k element is there, less than k element will be going to the left, and greater than k element will be going to the right. That is called as 2 trees. Okay, and it is a binary tree. It's just the condition is that it should have 2 children, at most 2 children. Okay, the order in which they are going left and right, that is concerned with binary search tree. Okay, it is a sub part of binary tree. This is binary tree as domain. The sub part tree will be having binary search tree. Okay, so any node, whether it is less than in the left or right, it is more than, if you, even if it is the reverse happened here, it doesn't matter, it should have just 2 nodes in the at most 2 nodes. That means 0 node can be there, 1 node can be there, and 2 node in the children node. That trees is called 2 trees. 3 trees means that they will have 3 nodes. Okay, whatever is the element here, and we'll take 2 numbers, k1 less than k1 will be here, between k1 and k2 elements will be in the child node, and greater than k2 will be in the right side. So let's understand this using an example. Now 9 is here, you will take 9 only. 5 came after that, so we'll be assigning 5 here. Then 8 came, 8 also came here. 3 things can happen. When 3 things can happen, we have to divide into 2 parts. Okay, 2 things will be divided into, this one will become the left part, and this will become the right part, and this will become the main root. Okay, It became 859. Now next, what is the element? 9 we have done, 5 we have done, 8 we have done, 3 came. Now when 3 is coming here, what we'll do? It is lesser than 8, we'll go here. It is lesser than 5, yes. So we'll be assigning to the left part of 5. So it will become 3 5. Okay. Next, what is the element? It is 2. When 2 comes here, again the 2 will be assigned here. Whenever 3 happens, we have to divide it. And when we divide it, 3's left part will become 2 and 3's right part will become 5. Okay, and this will remain as such. But we cannot take the middle part and again keep here middle part and then 2 and 5 will come here. What will happen is whatever is the middle element, that will get attached with the top element. Okay, so when it gets attached with the top element, it will become 3 8, and left part was 2, so left part will be 2, and right part was 5, so right part will be here, and the previous right part will be taken into consideration from here only. Now again the same thing will happen. We will be getting the next element 4. When we will be inserting 4, it will become 4 5. That's fine. Then it will become 7. When it is becoming 7, we have 3 elements here. We have to convert this. So we will be taking the partitions here, and left part of 5 will be 4 and right part of 5 will be 7. Okay, so and 5 will be taken above. Okay, when we take 5 above, it will become in between. So left part is 4 and right part is 7. Done. Now what we can do is we can form the groups. Again these 3 elements are there. Whenever 3 elements are there, we have to divide it. Okay, so when we divide it, 5 will come here and left part will be 3 and the right part will be 8. Okay, and already we have the 4 and 2, right? So 3 will be coming here in the left part, which will be having the left as 2 and right as 4, and from here 8 will be coming, which will have in left part as 7 and right part as 9. So it will become like this. Okay, so this is called as a 2 to 3 trees. Okay, the next important concept is the heaps and heap sort. Okay, so I'll be telling you what all you need to know from the heaps and heap sort. What is it and how do you build it? Two approaches are there: bottom up and top down. And then we have the insertion and deletion in the heaps, and then we'll be using these properties to construct heap sort. Okay, so let's discuss each one by one. The first thing you need to know, what is a heap. Okay, heap is nothing but a binary tree. What do you mean by binary tree? Binary tree is nothing but node which has two children, and that node also at most it has two children. It can have one children or zero children as well. But it is not just a binary tree. It is a almost complete binary tree. What do you mean by almost complete binary tree? Suppose that I am starting to make a tree. Okay, I'm making like this. Okay, I'll be always starting the nodes from the left side. Okay, left side it is filled, then I'll go to the right. Then again I'll start from the left, then I'll go to the right, left, then I'll go to the right. Like this, if I do in this order, this is called as almost complete binary tree. Okay, it is not completed, but it is almost complete. Okay, and the order is followed here. The order should be followed while constructing the heap. Okay, then only it is called as a heap. Otherwise, it is not a heap. Suppose that instead of following the order, I made it like this. Okay, I'll made it like this and this one. I missed this one. Okay, I should not have missed this one, because until and unless this is filled, I cannot go here. Okay, that is also a criteria. Okay, suppose that I had a tree like this, then I did like this. Okay, so this is also not valid. How did I fill it here? I had to fill it here. Okay, that was the criteria. So this is not a heap anymore. Okay, if I had filled it like this, okay, then I did it like this, then only it is a almost complete binary tree, which is also a heap. Okay, that is the first criteria, which is the ACBT, almost complete binary tree. It should be having a structural property. Second thing is very simple, which is have it should have the ordering property, which is parent should be greater than child. If you see an example here, in every node the parent is greater than the child values, parent is greater than the child values, parent is greater than the child values, right? So this is a ordering property is satisfied here. This is how you will be constructing a tree, but there are some rules you need to follow. Okay, so let's discuss what are those rules. Okay, these two properties should be satisfied, but there are some rules to be followed. Let's discuss what are the rules. Okay, now see, just see what I'm telling. Okay, don't see these things and get confused. Okay, this is the elements which you have given. Okay, in the exam they can give you these elements and they can ask you to construct a heap. Okay, so how do you construct a heap? So first thing what you need to do is, whichever the elements they have given, start making a tree. Okay, 2. Next, 9 is given. So first left part I have to fill. Then 7 is given. I have to fill the next part here, right part. Then 6 is given. So since these two are done, I'll be filling the children of 9. Okay, so it will be 6 here. Next 5 is present, so I'll be filling 5 here. Next 8 is present, I'll be filling 8 here. This thing is the first part you need to do, construct a almost complete binary tree. So after this part you have to do some comparisons. Okay, using bottom up approach, this is the most widely used approach. Okay, we'll be using the bottom up approach only. Top down approach we'll be using for insertion and deletion, that I'll be discussing in the upcoming topic. First step you need to do this. Okay, you have got this one, you have done this one, and if you observe carefully, this thing is same as this one what is given here, right? Next what you will do, after you have done this much, you have to start the comparison from the bottom, because this approach is called as bottom up approach, right? So you'll be starting comparison from the bottom. What I told you, the criteria should be the root element should be the largest and parent element should be the largest among all the means if we compare with the children. Okay, right? That's the criteria. So here is the criteria fulfilled. How many parent child are there? This is the first parent child, second parent child, third parent child. We will start from the bottom level, okay, and start from the right. Now this is not filling the criteria because parent is smaller and child is greater. Just exchange it, okay, exchange it, and this one is satisfied. Now the criteria is satisfying. Next, compare this one. This is a parent, these two childs are there. Is parent greater than two childs? Yes, so these both criteria are fulfilled. So at one level, when the criteria are fulfilled, move to the next level. When you move to the next level, here again there is a parent and two child are there. And is parent the largest among the two children? No, it's not. It is the smallest, in fact. So we have to exchange. Okay, how do we exchange? Observe carefully. We will exchange like this. Okay, we'll compare 9 and 8, okay, with 2. Is 9 greater or 8 greater? 9 is greater and 2 is smaller, right? So we'll exchange 9 and 2. Okay, whichever is greater, that we have to exchange. Okay, so 9 comes here and 2 will come here. Okay, 9 came here and 2 came here. 8 will remain as such. Okay, now the criteria is fulfilled here. But since we made a change here, whether this one is still fulfilling the criteria or not. Previously it was 9, so it was fulfilling the criteria, but 9 has been gone here and 2 has come here. This parent child relationship, is it still satisfying or not? We have to see. 2 is greater than the children? No, it's not. So we have to exchange it. Which is greater element? 6 or 5? 6 is greater. So exchange 6 with 2 and keep it here. So exchange with 6 with 2 and 2 will be here and 5 will be here. And again, when 6 comes here, 9 and 6. Is it fulfilling the criteria? Yes, it is fulfilling. So this is a heap which we have constructed using bottom up approach. Okay. So this is the thing you need to know. And this is the algorithm. Okay. And algorithm will be having a for loop. This is the for loop which will be taking from top to down. Okay. I mean, for constructing the heap. Okay, means the first thing which you need to do, take the elements and construct the heap. Okay, so we'll be doing that, and this part of code is for comparison. Wherever it is smaller or greater, we have to exchange. Okay, so basically we are exchanging. If we are comparing h of j and is less than h of j plus 1, in that case we are making the change which is exchanging the parent and the child. Okay, if you write this algorithm 2 to 3 times, you'll be able to understand. Don't go behind this one like trying to understand and tracing the algorithm. It will take a lot of time. Okay, if you want, you can go through it, but the thing is, you need to understand this algorithm, and this one is a pseudo code. You can by heart it and write in the exam as such. Okay, understand this algorithm and write this, you'll be getting the full marks. Okay, next is the top down approach. This is the second approach. Okay, here the two things are there, insertion and deletion will be doing. Okay, now insertion means what? Inserting a new element. Okay, already a tree is constructed, we have to insert a new element. Heap is already there. Okay, this was the heap which we had in the previous problem. If you observe carefully, this is the heap which we had in the previous problem. Okay, it is same. We have obtained this one. Now I have got a new element which is 10. We have to add 10 to it. Okay, to add 10 to it, what we'll be doing is, this thing is here. Okay, we'll be comparing 8 and 10. Okay, when we compare 8 and 10, we have to exchange it. Why? Because 10 is greater and 8 is smaller. Okay, and 7 is here. 7 and 10 also, 10 is greater. We will exchange these two. When we'll exchange these two, what will happen? 10 will come here, and this criteria is fulfilled here. So this we did not touch, we will not touch again. Okay, so here the changes happened here. Now we have to compare 6 and 10, which is greater. 10 is greater and 9 is smaller. So again, to fulfill this criteria, we will exchange 9 and 10. So the final tree will look like this. This is the way we insert an element using top-down approach. Second is deletion of the element. To delete an element, what we'll do? First, if you want to, suppose you want to delete 9, okay, whichever element you want to delete, you have to exchange with the last element. Okay, whichever element you want to delete, you have to exchange it with the last element. Okay, last element here is 1. Okay, how do you get to know if it's the last element or not? The way in we construct the almost complete binary tree, first it will be this, then this, then this, then this, right? So if an element was here, 9 would have been exchanged from here, but since this is the last element, we'll be exchanging 9 from here. What do you mean by exchanging 9 from here? Exchanging 9 from here means put 1 here and put 9 here, that's it. Okay, put 1 here and put 9 here, that's it. Now after doing this one, what you have to do is, you have to apply the heap sort. Okay, I mean the criteria for the comparison thing. Okay, now here, since 9 is coming here, we'll be removing 9 from here, that's it. Okay, now we will be applying the algorithm, which is the comparison. Okay, here is the criteria getting fulfilled. 2 8 and 5 8, yes, it's getting fulfilled. Child is smaller than the parent. Next, at this level, is it getting fulfilled? 8 and 6 is smaller than 1. No, it's not. So which is greater? 8 is greater, so 8 will be exchanged with 1. When 8 will be exchanged with 1, 8 will be here and 1 will be here. Okay, and 6 will remain as such. Now again, here 1 is there. 1 is greater than 2 or 5? No, it's not. So 1 has to be exchanged with 2 and 5. with which it will get exchanged. With 5 it will get exchanged because 5 is greater. So 5 will come here. Okay, 5 will come here, 1 will come here, 2 will be here only, and here what will be having 8. So 8 5 1 2, 8 5 1 2. This is the thing which we'll be doing for the deletion. Okay, so two things we have discussed. In the top down approach we have the insertion and deletion. Now with these concepts we'll be discussing how do you do the heap sort. Okay, that also question can be asked in the exam. To do heap sort, first you have to create a heap. Okay, without a heap how will you do heap sort? If you don't create a heap, there will be no heap to sort. Okay, so you have to create a heap first using the same criteria. Okay, I'll discuss the example, you'll understand. Then delete the nodes one by one, because deletion is important. The way in which we delete the elements, that will give us the sorted order. Okay, the way in which we delete the nodes, which will give us the sorted order. Now example we'll take 4 6 10 9 2. Okay, just create a normal heap. Okay, how do you create a normal heap? 4 will be assigned here, then 6 in almost complete binary tree style, 9 will be assigned here, and 2 will be assigned here. After that, do the comparison. Here in this child, here child parent relationship, is it satisfied? No, it's not satisfied. Why? Because here 2 is present, then here 2 is present, and here 6 is present, and then here 9 is present. Okay, so here we are doing the min heap. Okay, there are two types of heap. One is the min heap and second is the max heap. Okay, so if you want to do it in the ascending order, you're using min heap. If you want to sort in the descending order, you'll be using max heap. Basically min heap and max heap are same, just that whatever I discussed till now, that was the max heap. Okay, and what do you mean by max heap? In max heap, the root element will be the largest. Okay, that is the max heap. If root element is the largest, that is the max heap. And always we'll compare, the parent should be greater than the child. Okay, parent should be greater than child, parent should be greater than child, that is the max heap. But here we are doing using min heap. Why? Because we want ascending order. So basically the parent should be lesser than the child. Okay, that's the criteria, and root element should be the lowest element. Okay, so here we'll start from here. Is parent lesser than child? No, it's not. It is greater because there is 2 here, right? So 2 should be here. Okay, so and the smaller among 9 and 2 is 2, so we'll exchange 2 with 6. When we exchange 2 with 6, we'll be getting this here. Next, again 2 10, 2 and 10 is here and 4 is here. Is the parent lesser than the child? No, the child is lesser, so this has to be exchanged. When we exchange these two, what we will be getting? 4 will be getting and 2 will be getting here. Now this is the thing which you need to do in the first step, where you create a heap with the min heap order, because you want ascending order. If you wanted descending order, you would have compared which one is greater, and then you would have done as we had done in the previous case. But now I have got 2 here. Now 2 is the element. Observe carefully, in this all elements 2 is the smallest element. Because of our algorithm which we applied, 2 we got the smallest element. So if you want the ascending order, this should be the first element, so we have to delete this node. When we delete this node, we'll be taking into consideration. Okay, then delete node one by one. We are deleting 2 here. Okay, 2 we have deleted. So since 2 is deleted here, what I told you, if you want to delete some element, you have to exchange it with the last element. Okay, last element is 6, exchange 6 and 2 and then delete 2. Okay, so 6 came here and then 2 is deleted. Okay, now again apply the algorithm. Here the parent child is there, the parent is smaller than child, done. Here the parent is lesser than child, done. Is the parent lesser than child here? No, 6 is not lesser than 4. Okay, so we have to exchange this one. When you exchange this one, you'll be getting 4 and 6 here. Now this is a sorted one. Okay, this is a min heap. Now 4 is the smallest element here in this whole heap, and we'll be deleting 4. When you delete 4, what I told you, exchange it with the last element. Last element is 9, exchange it with 9, so 9 will come here and 4 is deleted. Now again, parent is lesser than child. Yes, parent is lesser than child. No, exchange these two. When you exchange these two, 6 and 9 is here. 6 is the least element, delete 6. When you delete 6, what I told you, exchange it with the last element. In this criteria, last element is 10, so exchange it with 10. So when exchange with 10 here and delete 6, you'll be getting 10 here and 9 here, 10 here and 9 here. Again, is this criteria fulfilled? Yes, the criteria is, no, sorry, the criteria is not fulfilled, because 10 is greater and 9 is smaller. Okay, 9 should be here, right? When we exchange these two, we will be getting 9 here. We will be deleting 9 and we'll be remaining with 10, which is the last element we'll be taking into consideration. The way in which we deleted first smallest element, second smallest element, third smallest element, fourth smallest element, and fifth smallest element. So smallest to greatest we are deleting. This is called as ascending order. So the order of deletion will be taken into consideration, and that will be the ascending order. So this is the min heap if you want ascending order. You will do the max heap formula if you want a descending order. That's all you need to know about the heap sort. In the exam, if they give the question, you have to apply in the same way. Okay, just observe carefully if they're asking ascending or descending. Okay, next is the sorting by counting, or here comparison sorting count. Okay, we'll be doing the sorting using comparison. Okay, so how does this work? Okay, in comparison and sorting count, the elements are compared and given ranks. Okay, elements are compared means if 1 and 2 is there, we are comparing 1 and 2, and then what we are doing, we are ranks based on greater than. Okay, let's say understand this using an example. Now this is 647. Now 62 is present here. Can you tell me how many elements here are lesser than 62? Is 31 lesser than 62? Yes. 84? No. 96? No. 19? Yes. 47? Yes. So three elements are there which is lesser than 62, 31, 19 and 47. Okay. So you'll be writing 3 here. The count you will be writing. How many elements are smaller than this one? How many elements are smaller than 31? Smaller than 31, how many elements are there? Only one element, 19. So we'll be writing 1 here. Okay. And then I'll be telling you how do you construct this. Okay. But first understand what is this. Okay. Next, 84. How many elements are lesser than 84? One element here and two element, three element. Three elements are, sorry, four elements. 62 is also lesser than 84. So four elements. You'll be writing 4 here. Then 96. How many elements are lesser than 96? Five elements because all the elements are lesser than 96 here. 5. 19. How many elements are lesser than 19? None of the elements. 47. How many elements are lesser than 47? 31 and 19. Okay, so two elements you'll be writing here. Now, we have written this one, but here some other elements are there. How does this work? Okay, that one I'll be telling you. Okay, now I'll be telling you before that. These value which I have got in diagonal, write it in the last state. Okay, now what is the thing is the numbers we have got. Okay, see, suppose 19 lesser than 19 there is no element. What does this indicate to you? This indicates that 19 is the least element, right? So 19 will be in the zeroth index. Next, which element has one element lesser than it? 31. 31 has only one element lesser than it. That means 31 is in the second smallest element. Next, 47 has two elements lesser than it. That means 47 is the third smallest element. Like that, based on the values which you have got, the 3 means it will be stored in the third index. I mean 0, 1, 2, 3, 4, 5. It is in this way, okay? So 3 means it will be stored in the third index. 1 means it will be stored in the one index. And 2 means it will be stored in the second index. Like that, okay? Whatever the values we have got here, compare it with these elements and store it in these indices values. This way of comparison is called as comparison sort. Now, how we have written these things, okay? Now see, first stage you write all zeros, done. Next stage what you will be writing is you'll be comparing, okay? 62 and 31 you will compare. When you compare 62 and 31, which is greater? Whichever is greater, increment that count. Okay, so when you increment that count, initially it will be 0, right? Incremented that count, it will become 1 here. Okay, now 62 84, which is greater? 84 is greater, so increment 84's count. 62 and 96, 96 is greater, increment 91's count, 96 count. 62 and 19, 62 is greater, increment 62's count, so it is 2 now. 62 and 47, increment 62's count, 62 is greater, so it will be 3. After this complete iteration, whatever we get the value for which element we are comparing, that will be the final answer for that. So when you compare 62 with all the elements, 3 elements we got smaller than 62, so the value assigned to 62 is 3. Done. Got the point. Now 31 we had got 0 elements because we compared, none of them got. 84 we had got 1 because we had compared these two, right? At that time we had put 1 here, and also this 2 we had compared, we had got 1 here, right? These two were 0, so 1 and 1 which we got here, that is 1 and 1 written here, rest always 0. Done. Now after you have done this one, take into consideration the next element, 31. Compare, you will be comparing now from the right only, okay? Because this is done, okay? 62 is done. Now we'll be comparing to the right. Now we compare 31 with 84, which is greater? 84 is greater, so increment 84's count. 84 initially was 1, now it became 2. Okay, now 31 will remain 0 only. 31 with 96, 96 was initially 1, it will become 2. Okay, this is greater. 31 with 19, which is greater? 31, so 31 was 0, it became 1. Now 31 with 47, 47 is greater, so 47 was 0, it became 1 here. Got the point? This is how we get these elements. Now 31 is also done. Compare 84 with all these elements. 84 with 96 when we compare, which is greater? 84 or 96? 96 is greater, so increment 96 count, 2 to 3 it will become. Okay, 84 with 19. 84 is greater, so 2 will become 3. Then 84 with 47 will be compared and 3 will become 4. Okay, so final value is 4 here. So 84, 4 values is sent. Like that only we keep on doing till the end. When you get these values, we'll be putting it in the array in the indexes of this, whatever indexes are here, those elements will be putting in those respective indexes, and we'll be getting the final answer. This is the comparison sorting. Okay, you need to understand this. If they give in the exam an example, you have to do it in this way, make this table of this kind and write the answer. Okay, and this is the algorithm, you can go through it. This is a triple for loop here. First is for getting the count of the elements, and then you will be getting the inner double for loop for checking. Okay, First is to assign the count, and second, see, all zeros are assigned, right? That is the first one. Count of I is equal to 0. Okay. After that, this is a double for loop because each element is getting combined with this, then with this, then with this. So that's a double for loop. Obviously, I is equal to 0 to n minus 2, j is equal to I plus 1 till n minus 1. Okay. We'll compare, and whichever is greater, that count will increment. Okay. If j is greater, we'll increment the j. If I is I is more, we'll increment the I. Next, after that, assign those indexes in the main array to a of I. Like what we are doing here, basically this value we have got here, some value. Okay, so 62 has to be assigned in third index, so the main array is S array. Okay, so S of 3 should be 62, so S of 3 is the count, should be 62. 62 is a of I. So in this way we will be assigning the final array also. Okay, write this algorithm 3 times, you'll be able to keep in mind. Okay, moving on to the last topic, which is Horspool's algorithm. Okay, this is also very simple algorithm. Let's understand using an example. Okay, so here the pattern given is barber and another text is given. Okay, like some sentence is given. Okay, like I am a Barbie and a barber. Okay, like that. Now we have to search in I am a Barbie and a barber. In that we have to search barber where it is present. Okay, so we will be comparing barber with each of these elements. Like barber is present in the starting one or in the middle one, where it is starting from and ending. That wherever we find, we'll be highlighting that one. Okay, so the Horspool algorithm is for searching this text in the main text. Okay, that is a string matching algorithm. Now some rules are there. We start comparison from the right to left. Okay, right to left we'll be comparing. Now you can see a C here. What does this C mean? C is nothing but the element at that instance. Okay, whatever is the sentence, that sentence is here, and we are comparing the text with this sentence starting from here, and whichever letter is present here, that is denoted by C. Okay, C can be any letter A to Z. Okay, it is a variable which denotes a letter which is present in the main text at this point of time. Okay, so we'll be comparing this one with this one. Now C can either be, there are two scenarios. Whatever we get here, that can either be R or it can be any other letter from A to Z. Okay, any other letter from A to Z or R. If it is R, means these two have matched. Next we have to match these two. Okay, then we'll compare. It can be either E or any other elements. If it is E, we'll go back here, we'll compare. If it is B, go back. R, A, B, we have got till here all the elements. So the actual thing which was written here was barber. Okay, and one by one we will be assigned the variable C here and compared here, and all of them got satisfied. So barber is found at this point. That is the ideal scenario, but always it will not be same that this will be R, this will be E, this will be B. There can be some other elements. For example, if this was not R, this was S, C was pointing to S here. In the main string there was an S here, and R was here. Okay, S means gas. Okay, suppose that the some sentence was there and gas has been compared with this one. Okay, R and S, is it same or not? It is not same. So if it is not same, there will be arising two scenarios. If it is same, there will be arising two scenarios. So totally four scenarios will be arising if it is same or not. Okay, two for same, two for not same. What we have to do now, let's have a look at the four scenarios. The four scenarios is, in case, okay, we have started comparison from here. Start the comparison from this point. R is here and S is here. Okay, we have got S here, but we know that we have to find R. Okay, now S, is S of any use to me? Okay, this S is not at all present here, so this S cannot be matching this algorithm when it is included. So we have to start from the next part of it. Means after S you have to start the comparison, because until and unless S is there, it will never match this pattern, because with S this pattern cannot be matched. There is no S in this pattern, so we'll be starting comparison from here. Okay, so that is the thing. We had a letter here, and since we got S is not present, we'll be starting comparison from here. That's the first case. Second case is that we have got a comparison here. B came, but R is here, and B and R both are not same, so we have to shift all the letters. No, we have not shift all the letters. We have to see if B is present in the text or not. What if the B was present here? What if B was present here? B is present here, so we'll be aligning this B with B. Okay, so when we shift it, and this B will get aligned with this B. Okay, so what if this thing was like this? Okay, suppose okay, BAR BER. Now this B had not matched with this one, so if we had put all the B's from here, so it will become BARBER. So in that case we would have missed the letters. Okay, see, barber was present here. You get the point, right? Barber was present here, but we started comparison from here, but so we missed it. So in order not to miss it, we have to check if B is already present here or not. And since B is already present, we'll be assigning B here and checking what if the letter was this one, BARBER. Okay, in that case this word will be found here, so you have to assign it if it is present in the rightmost side. Okay, we'll be going from here, and first element, when you found the same element as this, align it with this. Align means B will be here and all the letters will be shifted. That's the second case where it is not same. Okay, first case when it is not same, you have to do this. If the element is not there, only start comparison from the next part. If it is there, start from that point. Okay, means align it with this. Okay, next is, suppose we have got here R. R is present, done. E is also present, done. Now M is present and D is present here, and M is not at all present here. That means M cannot be found here. Unless and until M is there, we cannot move forward. Okay, so since we cannot move forward until and unless M is there, you have to shift all the elements here. Okay, if you get an element which is not compared, we'll be shifting all the elements, so leader will be starting from here. That's the third scenario. Okay, fourth scenario is, if it happens to be the, see what happens, R is here, done. Now A and E, it's not same. Okay, so since R was here, we'll be assigning the next R. Okay, which is the next R? Next R is here. Okay, so we'll be aligning this R with this R. So when you align this R with this R, we'll be getting this R here. Okay, and the other elements will be shifted, and then again it will be compared A and O. That's the secondary scenario. But first scenario is you have to align R with this R. Okay, wherever a letter is present, rule is very simple. If the element is same, compare the previous element. That is also same, compare the previous element, go on till you reach the end. If it is not same, check if this element is there in the previous there or not. If it is there in the previous, align it with that and continue the comparison. If an element which I am searching that is not there, like X, it's not there in this, if it is not there, start comparison from the next part. Okay, these cases are just for the theory part you need to write. Okay, understanding is more important. Okay, once you understood, you can write this theory in your own words also. Okay, so next, the exam type, what question could be asked. Okay, this is the July 2024 question paper exam question. So here, design Horspool algorithm for string matching. I'll be showing the algorithm that you have to learn, and then apply this algorithm to find the pattern barber in the text. Okay, so this is the main text given. Jim saw me in the barber shop. Okay, most of the exam papers this same question gets asked. Okay, and this is in the textbook also, so learn this very well. Okay, so you'll understand how to solve this problem. Okay, so let's take here. Okay, first thing, you need to write the text again in the exam. Okay, don't become lazy, it's already there in the question paper, why should I write? You should write. Okay, so here the pattern will be writing here. Okay, after you have written this one, write it from the start. BAR. Okay, you have written this. Next step, compare A with R. Okay, last you have to compare, means from right to left you have to compare. So A with R, is it same or not? You have to answer me some questions. Okay, I'm asking you, is it same or not? A or R, is it same or not? It's not same. It's not same. Second thing I need to see is if A is already present in this or not. Yes, A is already present here. So I have to align A with this. So I'll be aligning A with this, and rest of the elements I'll be shifting. A is aligned with this. Whatever is behind that, I'll be writing it here, and I'll be writing the further elements here. BAR, BER. Done. Next, I'll be comparing E with R. Is it same or not? No, it's not same. What's the second thing? See if E is present here or not. E is present here. Yes, it's present. So align it with this. When you align it with this, E will be coming here, R will be here. Okay. Then we'll be writing the previous elements, B, R, A, B. Okay. B, R, A, B. Okay. Now the element which is present here is the space, and space is compared with R. Okay. And space and R, is it same or not? Space and R, it is not same. And second criteria, is space present in these elements? No, it's not present. So when space is not present in these elements, shift the whole thing from here. So barber will be starting from here. B A R B E R. Then again compare. B with R, is B equal to R? No, it's not. Where is the previous B present? Previous B is present here, so align it with that. Okay, so B E R will be writing here, and the previous elements R A B will be writing it here. Okay, now R R. So first element we have got here as equal. Okay, next what you have to do, compare the next one. A and E, is A and E present or not? A and E, is it same or not? It's not same. So A is present or not? A is present. Where is A present? A is present here, so align it with that. When we align it with that, we'll be writing this element B will be writing same, E is the final text. Yeah, this is okay, along with the algorithm C. So this is how you solve Horspool algorithm. Okay, Now, in the theory part, what you have to write in the if they ask in the exam the theory part, okay, like write the algorithm, write the shift table, what it is. Okay, I have not discussed about the shift table till now because without shift table, without using shift table, if you can do the answer and you'll be getting the marks, what is the point of knowing about the shift table? Okay, but the theory part is important. Okay, so shift table is used when we write the code algorithm and all. Okay, because computer won't solve the way we solve. Okay, so they need the shift table. So basically, what is a shift table? The thing which I showed you, right? How many elements should be shifted? The criteria I told you, right? If it is same, means if it is same, compare the previous one. If it is not same, check if this is present here or not, and wherever it is present, shift that many elements. That thing, okay, whatever I told you verbally, that has to be coded. Okay, that is only the shift table. So shift table will denote how many characters has to be shifted. Okay, so if the pattern's length is m and C is not among the first m minus 1 characters, okay, means C, whatever we have found, that is not there in the list. Okay, like X we have found, X is not there. You have to shift what? Shift all the elements of the length. Okay, next, if the distance from the rightmost C is among the first m minus 1 characters, that means I found A and A is somewhere here. How many shift you have to do? You have to shift between this difference. Okay, what is the difference here? That much you have to shift. That is the second criteria. These two criteria you write for the shift table. Next thing you need to write the shift table algorithm. Okay, so here the input is a pattern and the output is a table. Okay, now shift tables criteria is we got a pattern, we have to output the table. Okay, how does this table work? From I to 0 to size minus 1, table of I is equal to m, j is equal to 0 to m minus 2, table of p of j is equal to m minus 1 minus j. Don't try to understand this one, it will take a lot of time. Okay, just remember this one and write in the exam. Okay, you'll be getting the full marks. And don't worry if you write something different here, like you suppose you write n, here you write 2, it doesn't matter. Okay, they won't check that much. Okay, you have to write something here which looks like a equal formula. Okay, so what I'm trying to say is spend more time understanding the concepts. Okay, not by hearting the things. Okay, so write something similar, you will be most probably getting marks. Okay, next is Horspool algorithm. Here also the input is the pattern and the text, both are the inputs. Output is the index where we have started matching the algorithm. Okay, shift table first you'll be calling it, and then there is a while loop inside which there is another while loop. Okay, comparison is done here. So basically this comparison denotes what we had done here. If a shift is to be required, if a shift is required, we'll do it from here because we'll be having how many shifts is done. If it is not there, we'll be keep on going, and unless and until we reach the end. If we k is equal to m means the pattern is matched, we'll be returning I minus m plus 1, which will denote which index it was matched. Okay, that's all for this video. If you found this video helpful, please like and subscribe. It helps me make more videos like this, and don't miss any of these concepts. And thank you so much for watching. I'll see you in the next one.